Moving on into the second section of our review. This is a section that talks about radians, degrees, as well as arc length and sector area. Starting off with converting degrees into radians. The way you convert from degrees into radians, if you forgot, is you multiply your degree angle by pi over 180 degrees. And the way I remember that fraction is you multiply by pi over 180, because if you think about your unit circle, 180 degrees and pi are the exact same place. This is 180 degrees. It's also pi radians over there at that 180 degree mark. You want to use angles that are the same. Pi radians is the same as 180, so that's where the pi over 180 comes from. So for number 8, if I'm going to convert 50 degrees into radians, I'll simply multiply by pi over 180 degrees. And whatever you want to be left with, like I want to be left with radians, so radians goes in the numerator of what I multiply by. So here the degrees cancel, and 50 and 180, you can cancel those zeros, and that leaves you with 5 pi over 18, and that would be your answer, 5 pi over 18 radians. For number 9, I'll just do it down here. We have 220 degrees. I'll do the exact same thing. We're going to multiply by pi over 180, and we'll start reducing. Let's see, degrees cancel. The zeros cancel. And this is going to start looking messy here, so I think I'm going to go ahead and multiply that. It's 22 pi over 18. And then I'll look at that, and 22 over 18 reduces again. 2 goes into each of those. 2 goes into 2 goes into 18 9 times. 2 goes into 22 11 times. So we're left with a radian measure of 11 pi over 9. And then the last one, 175, number 10. 175 degrees, we would multiply by pi over 180. And let's see, degrees cancel. 5 goes into each of these. I know that much. We'll see 5 goes into 175. See, 5 into 17 is 3. That leaves you 15. 3 times 5 is 15. 17 minus 15 is 2. Bring down the 5. 5 goes into 25 5 times. So 5 goes into 175 35 times, and 5 goes into 180. That's going to end up being 40. So we're left with, did I do that right? 35 pi over 40, which reduces, again, 5 goes into each of those. 5 goes into 35 7 times. 5 goes into 40 8 times. No, 5 doesn't go into 180 40 times. I knew that didn't look right. I'm stupid. 5 goes into 180 36 times. My bad. And so we're down to 35 pi over 36. Let me double check that since I messed up. 5 into 180, that's 3, 15, 18 minus 15 is 3, bring down the 0, 5 goes into 36 times. So yeah, that's right. So we get an answer of 35 pi over 36. Good. Be careful with your work. And also, I could have used calculator on these. I didn't notice that these were calculator active problems. Okay, let's see, going the other direction, converting from radians to degrees, we're going to use the same conversion. We know pi degrees or pi radians is the same as 180 degrees, but in this time, since I want to be left with degrees, my 180 degrees goes in the numerator, and my pi radians goes in the denominator. So when I multiply these, number 11, we've got 4 pi over 5. We would multiply by 180 degrees over radians, over pi radians, and then we start canceling. Let's see, pi goes into pi, or pi cancels pi. 5 goes into 180 degrees. We just did that. 5 goes into 180 36 times. And now I'm left with 36 times 4. So 36 times 4, I think it's going to be 144. That's 24, carry my 2, 12 plus 2 is 14. So yeah. So we get an angle of 144 degrees for number 11. Number 12, we have 7 pi over 9. We'll multiply it by 180 degrees over pi. When you're converting to degrees, you put the degrees in the numerator because that's what you want to be left with. The pi's cancel. 9 goes into 180 20 times. So we're left with 20 degrees, and 7 times 20 is 140 degrees. You good? Same thing for 13 pi over 6. 13 pi over 6 times 180 degrees over pi. Then we start canceling. We'll see pi cancels pi. 6 goes into 180 30 times. And now we have 30 times 13, which is 390. So we have 390 degrees for number 13. A little bit bigger than the whole circle, but that's fine. You can have an angle over 390. Just remember that an angle over 360 means that I started here and I went all the way around 360 degrees plus 30 degrees more. So that's what an angle of 390 degrees would look like. I'm just thinking, you didn't have to draw that out. I'm just kind of showing what it means when you have an angle that's so large. All right, let's see, moving on. Find 2 coterminal angles for the given angle. And then if you remember what coterminal means, it means 100 degrees means that I started at 0 over here and I opened up 100 degrees. That's 90, so 100 is about that much right here. So this is 100 degrees. And what we have to do is we have to find 2 other ways to get to this same location. And our options are, to me, the easier one to see is instead of opening up counterclockwise, let's go the other way. Let's go backwards. Let's go backwards. That's 180. And if I keep going, if I go backwards that whole angle, I would be at that same place. And the way we find that angle is you simply take your first angle, which was 100 degrees, and we subtract 360. And that would give me an angle of negative 260 degrees. And that's what this angle is right here. So that's negative 260 degrees. And that would be one of the coterminal angles, negative 260. The other way I could get back to 100 degrees, or get to that same location, is I could open up 100 degrees, but instead of stopping at 100, I could go all the way around the circle one more time, and I'll still end up at that same place. So 100 degrees plus the entire circle would be 100 degrees plus 360. So my other coterminal angle, starting at 100 degrees, I would add the whole circle. That would give me 460 degrees, and that would be the measure of the angle that went all the way around the circle and a little bit more. So that is our other coterminal angle, 460 degrees. Okay, good? Good. And the way you find the 2 coterminal angles is you simply take the angle you're given and you add 360 and you subtract 360. Or in the case of number 15, you're in radians, so we're going to add 2 pi and subtract 2 pi. So to get my 2 coterminal angles for pi over 3, I'm going to do pi over 3 plus 2 pi, and my other one is pi over 3 minus 2 pi because 2 pi radians is the same as 360 degrees. So we're still adding the whole circle. We do need to get a common denominator. This is 2 pi over 1. And common denominator for 3 and 1 would be 3. So let's see. This would be the same as 6 pi over 3. Pi plus 6 pi is 7 pi. And the denominator doesn't change when you add fractions. So 7 pi over 3. This one, again, I'm going to turn 2 over 1 into 6 over 3. Pi minus 6 pi is negative 5 pi. And my denominator doesn't change when you subtract. So there are the 2 coterminal angles for pi over 3. You're good? You're good? You're good? You're good? All right, let's see. Moving on. The length of the intercepted arc and the area sector. Okay, a few notes for you here. And we did this a while ago. Arc length. is your length is simply your radius times theta, and sector area, your area of the sector is 1/2 r squared theta, and you do need to remember that theta must be in radians. Your theta must be in radians. So those are the two formulas we're going to use. I give you the theta and the radius. So for number 16, my arc length is simply, you just simply multiply those two. It's r, which is 5, times theta, which is pi over 6. And when you multiply those, that's 5 over 1. So 5 times pi over 1 times 6. And there's your arc length, 5 pi over 6. Not too bad, is it? Area is a little bit more cumbersome. That's 1/2 of r squared. So 1/2 of 5 squared times the angle, pi over 6. And we do have a little bit more arithmetic to do here. That's 1/2 of 25. That's what r squared is. I'm going to put 25 over 1 so I can see all the fractions. Times pi over 6. And when you multiply that, 1 times 25 times pi is 25 pi. And 2 times 1 times 6 is 12. And that would be your sector area. And in case you've forgotten what we're talking about, what arc length and sector area means we're starting with the circle, and we have a central angle of pi over 6. And if you remember your unit circle, pi over 6 is about 30 degrees. So I would open up about a 30-degree angle. That looks about 30-ish. And I'll call this angle here pi over 6, and the radius of this circle is 5. Your arc length is this length right here. No, that's kind of fat. Let's undo that. Okay, this length right here is the arc length. That's what I got right here. That's a length of 5 pi over 6. And sector area is the area of this region inside. So it's like it's like part of the circle's area, but it's not the entire circle area. And so that's what we're talking about when we talk about arc length and sector area. Now let's see, let's knock out those other two. Number 16 or number 17. Your arc length is r theta, so that'd be 1.5 times theta, which is 4 pi over 3. I'll tell you what, I'm not a huge fan of decimals, especially if I have decimals and fractions in the same problem. So I'm going to change 1/5, 1.5. 1.5 is the same thing as 3 over 2. And I'm going to do 3 over 2 times 4 pi over 3. And then I'll start canceling. Ooh, this is sexy. Look. Now let's see. 2 goes into 4 twice. The 3's cancel completely. And I'm simply left with 2 pi for the arc length. So I have an arc length of 2 pi. And then the sector area is going to be 1/2 of my radius, which again I'm going to use my radius as 3 over 2 instead of 1.5. 1/2 r squared theta, which is theta is 4 pi over 3. And then we'll clean that up. So that's 1/2. You remember to do the exponents first. Please do not multiply before you do the exponent. 3 squared is 9, 2 squared is 4, and then 4 pi over 3. And again, we're going to have some canceling here. Let's see, this 4 is going to cancel this 4 completely. This 3 is going to go into 9 3 times, and I'll look at what's left. Let's see, 1 times 3 times pi is 3 pi. Over 2 times, and those canceled, so we're just left with 2. So there's arc length and area for number 18. Number 17. Number 18, you have to be really careful because notice my theta I gave to you in degrees, and you have to remember theta must be in radians right there. Theta has to be in radians. So what I'm going to have to do first on number 18 is convert 135 degrees to radians, and we have two ways we could do that. One way is to go through the old hassle, 135 degrees. If you want to convert that into radians, you would multiply by pi over 180. and you could get your answer. Or you could think about your unit circle, because 135 degrees is an angle on the unit circle, and if you know your unit circle, then you also know that 135 degrees is the same thing as 3 pi over 4 radians. So rather than go through and do the multiplication to solve that, I'm going to just think about my unit circle, and I know that 135 degrees is 3 pi over 4 radians. All right, so number 18, when I do my arc length, it's my radius, which is 3, times my angle measure, which is 3 pi over 4, and we'll multiply those. This 3 for the radius is over 1, so 3 times 3 pi is 9 pi, and 1 times 4 is 4. So 9 pi over 4 is the arc length. Sector area is 1/2 my radius squared, so 1/2 of 3 squared, times my theta, which is 3 pi over 4. Then we clean that up. That's half of 9, and I'm going to put that 9 over 1 so I can get the multiplication a little bit more easy. 1 times 9 times 3 is 27. Pi over 2 times 1 times 4 is 8. That does not reduce. So there is your arc length and sector areas for 16, 17, and 18. I think that's the last thing in this section. Yep. So there is all the stuff from section 4.2 in our book.